Lewis' concept does not explain the shapes of molecules. In 1940, this drawback led Sedgwick and Powell to come up with a theory to determine the shape of a molecule. The shape of the molecule is based on the number, type, or extent of repulsions between electron pairs present in the valence shell around the central atom respectively. This theory is named as valence shell electron pair repulsion theory, or the VSEPR theory. It was further developed and redefined by Gillespie and Nyholm in 1957. The valence electron pairs surrounding the central atom in a molecule mutually repel with each other. Thus, these electron pairs surrounding the central atom arrange themselves in space in such a way to minimize the repulsions, giving the molecule a definite geometry. The molecules in which the central atom is surrounded with only bond pairs, then it is said to possess definite geometry, as in case of BF3. As the electron pair is a negatively charged cloud, the bonded atoms move apart to minimize repulsions between the electron pairs. To minimize the repulsion, the distance between the atoms has to be maximum. To attain the maximum distance between the bonded atoms, imagine the valence shell to be a sphere and the electron pairs located on its surface at maximum distance from each other. The shape of a molecule depends upon the number of valence electron pairs and their arrangement around the central atom. The geometry of a molecule, in which the central atom does not have a lone pair of electrons, will be regular without any distortion. For example, the shape of a molecule with two bonded electron pairs around the central atom will be linear, with a bond angle of 180 degrees. The shape of a molecule with three bonded electron pairs around the central atom will be trigonal planar, with a bond angle of 120 degrees, and so on. In a methane molecule, 4 hydrogen atoms are bonded to one central carbon atom. Since the electron pairs have the same charge, they repel each other and try to stay as far away from each other as possible. As a result, all the 4 hydrogen atoms arrange at 4 corners of a tetrahedron, lying at equal distances away from each other. Hence, methane has tetrahedral shape. In the methane tetrahedron, the bond angle is 109 degrees 28 minutes. However, the geometry of the molecules gets distorted due to the presence of lone pair of electrons. Unlike bonded pairs that are shared between two atoms, the lone pairs of electrons are localized on the central atom. Due to this, they occupy more space, which results in greater repulsion. Thus, the geometry of the molecules with lone pair of electrons differ from the expected or regular geometry of the molecules having only bond pairs. In a molecule, the repulsion between lone pairs of electrons is always maximum. Thus, we can say that the repulsion between two lone pairs of electrons is more than that of a lone pair bond pair, which is greater than that of two bonded pairs. Assume a multiple bond to be a single electron pair. Therefore, the presence of multiple bonds will not affect the shape of a molecule. Now, let's analyze the shapes of some molecules with reference to their valence electron pairs. In ammonia, the central nitrogen atom has 3 bond pairs of electrons and 1 lone pair of electrons. The ideal geometry of the molecule with 4 pairs of electrons would be tetrahedral. However, the lone pair of electrons repulses the NH bonded electron pairs, thus reducing their bond angle to 107 degrees and giving the molecule a pyramidal shape. In a water molecule, the central oxygen atom has 4 bonded pair of electrons and 2 lone pair of electrons. We have seen that repulsion between lone pair, and lone pair bond pair is more than bond pair. Thus, the 2 lone pairs on central oxygen atom makes the molecule to distort from its regular geometry to bend or V-shape, making a bond angle of 104.5 degrees. A sulfur tetrafluoride molecule is seesaw-shaped as its bond angles are at an angle of 101 and 173 degrees. Due to the lone pair of electrons present on its central atom. The chlorine trifluoride molecule is T-shaped and its bond angle is 87 degrees and 40 minutes, and the molecule shape is distorted due to the 2 lone pair of electrons on central chlorine atom. In a molecule of bromine pentafluoride, the central atom bromine has 5 bonded pair of electrons and 1 lone pair of electrons. Therefore, the geometry of the molecule is distorted, octahedral, or square pyramidal. It is due to the presence of a lone pair of electrons on central bromine atom. In a molecule of xenon tetrafluoride, the central xenon atom is surrounded by 4 bonded pairs of electrons and 2 lone pairs of electrons. The geometry of the molecule is distorted to square planar from the regular octahedral geometry. It is due to the presence of 2 lone pairs of electrons on its central xenon atom.